I hope you enjoy this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. I also want to thank the Platonic Mystery School of the Divine Infinite Being for sponsoring this course, and you can check that school out at divineinfinitebeing.com. The Singularity gets its name, How a Star Becomes a Black Hole. On September 1, 1939, J. Robert Oppenheimer and his graduate student provided the first mathematical description of how a star could actually burn through its nuclear fuel, causing it to explode as a supernova, then gravitationally collapse into a point of infinite density, which Oppenheimer was the first to call a singularity. So it's as important. The fundamental equation we're studying is psyche equals singularity, and the point of infinite density got the name singularity by J. Robert Oppenheimer on the first day of World War II. Oppenheimer named the singularity on the first day of World War II, which he then helped to end as chief scientist of the Manhattan Project that created the atomic bomb. At the first test explosion at the Trinity site in New Mexico, he thought of a quote from his own translation of Krishna's Bhagavad Gita. "Now I am become death, the destroyer of worlds." So, this is an historically important event, especially considering that the name singularity was given to a point of infinite density by Robert Oppenheimer in a paper that he published on the first day of World War II, which he then effectively ended by helping the United States of America to develop the atomic bomb. He learned how to read Sanskrit, and he read the Bhagavad Gita in the original Sanskrit, so this translation is from his own mind. "Now I am become death, the destroyer of worlds." Usually the word death is translated as time. "Now I am become time," says Krishna, the destroyer of worlds. But at any rate, for this overall class, where we're studying the parallels between Platonic philosophy and the Vedanta philosophy, specifically of the Krishna-worshipping Vaishnava branch of Hinduism, I think it's historically important that the singularity got its name from this devotee, or at least student, of Krishna. Casimir effect, empirical evidence of the quantum vacuum. In 1948, the Dutch physicist Hendrik Casimir discovered a way to detect experimentally the theoretical vacuum energy. Casimir argued that the quantum fluctuations should cause two metal plates placed very close together to be pushed all the way together, because there would be less vacuum energy between them and more vacuum energy pushing on the outside of each plate. The experiment that proved the existence of the Casimir effect was conducted about a decade later and has been repeated ever since. Thus, quantum vacuum energy is an experimentally verified physical reality, which lends credence to the equations indicating that the vacuum may consist of tiny black holes tightly packed at the Planck length. So, an actual experiment was conducted that confirms the existence of vacuum energy. Vacuum energy, the mathematical equations that describe it indicate that it's made of infinitesimal black holes, which again is crucial for understanding the implications of the psyche equals singularity equation. So what he did was he put two plates close together down to the atomic scale, and the idea was that each quantum particle has a different wavelength of energy associated with it. And if you put these plates very close together, then some particles' wavelengths, which are too large to fit in between the plates, would therefore be excluded. They would only exist on the outside of the plates. So there'd be more energy on the outside of the plates, and it would push them all the way together, which did happen. So there is such a thing as quantum vacuum energy. That does lend credence to the mathematics which describe quantum vacuum energy as being infinite at every point, or in other words, a singularity at every point. Multiverse, many worlds interpretation of quantum mechanics. In 1957, Einstein's protege, Hugh Everett III, theorized that although it appears that the wave of probability collapses into a single point when it is observed, in fact, each point in every wave of probability bubbles into a separate parallel universe. Susskind equates Everett's many worlds interpretation of quantum mechanics with his own string theory. He said, "I believe the two versions are complementary versions of exactly the same thing." The only difference between each universe popping out of each wave of probability is the position of one particle in that one wave. The accumulated effects result in an infinite variety of alternate universes, leading Susskind to ask, for example, what if Germany had won World War II? So, the multiverse theory is another one of these theories that emerges from quantum mechanics that has enormous philosophical implications. Obviously, if there is an infinite variety of nearly perfect carbon copies of each of us, performing our cosmic heroics in parallel universes that are branching off at an infinite rate, that's going to shape the cosmic stage upon which you're performing your heroics. So let's just chip away at this idea, which is going to be coming back again and again throughout this class. So Hugh Everett III was an American in Texas, and Einstein saw him as the future of physics. Einstein didn't like quantum mechanics, but he liked Hugh Everett's ideas. I know a little bit of the background between their relationship, but let me just focus on this slide. So in every wave of probability describes all of the points where a particle might appear were that wave to be observed. It would collapse somewhere in that wave to the particle that you would observe. So Hugh Everett III, he asked, well, what happens to all those potential points in the wave when the wave collapses? Do they just cease to exist? They just never actually came into existence? They've always had to remain in the limbo state of probability? He says, no, the equations work just as well if you assume that every one of those particles does manifest as a real particle, that there is no collapse of the wave in any real sense, because all of the points in that wave of probability manifest in a parallel universe. When you add up all these minuscule differences, each parallel universe is almost exactly the same as the one next to it. That means there's an almost exact replica of you in your entire history. The only difference between the you in this universe and the you in the parallel universes that are immediately adjacent to this one is the position of one atomic particle in some wave of probability somewhere in the universe. When you add up all those infinitesimal differences, then they become widely divergent historical paths. Susskind asked, what if Germany had won World War II? He's saying that the mathematics of quantum mechanics indicates that in some parallel universes, Germany did win World War II. That's not fiction for him. That's an inevitability from the mathematics of quantum mechanics. I don't know if he would call it inevitable, but at any rate, one of the things we'll discuss later in this class is the idea of free will. How can there be free will if there's an omniscient God who knows the past, the present, and the future? And even if there is no God, but we just accept special relativity, how can there be free will if the past, the present, and the future coexist? Well, here's one way that I try to overcome the idea of determinism and free will. Any choice that you want to make, you're absolutely free to make. There's an infinite variety of choices that you can make, and you can make any one you want. But any one of these infinite choices that you choose correlates to some universe where that choice has always been determined. So the parallel universe theory in a multiverse of an infinite number of parallel universes, and we'll come back to the idea of whether or not there's an infinite number or merely an extremely large number of parallel universes, but you get the union of two extremes. Absolute determinism. Within every universe, the past, the present, and the future already coexist, they're already determined, and they exist specifically at the outermost horizon of each spherical bubble universe. But there's an infinite number of them, and you can freely choose any path in life you want, but that path will correlate to one of these parallel universes. So we're getting a little ahead of ourselves, but I want to give you a little bit of an idea of how we're going to relate these complicated ideas of physics back to the psychology of things that address fundamental questions like free will and determinism. Ring singularity, the Kerr solution. We're going over the history of the concept of the gravitational singularity. In 1963, we're going to see this Australian physicist Roy Kerr came up with another exact solution for Einstein's field equations for the gravitational field. And he came up with the idea that if a black hole is spinning, then the essential singularity will be a ring and not a point. Now that complicates the equation psyche equals singularity, but let me just read this and then I'll address the issue of a ring versus a point singularity again. In 1963, Roy Kerr discovered another exact solution to Einstein's field equations based on the assumption that a star collapsing into a black hole would be rotating at the time, causing it to contract into a ring-shaped singularity instead of a point. According to Michio Kaku, the opening in its center provides a potential portal to another universe. The infinite density of a two-dimensional ring singularity is still contained in the smallest three-dimensional space possible. It still has zero volume, despite the fact that it potentially provides something like a tunnel to another universe. The Schwarzschild solution to the field equations of general relativity, which he came up with on December 22, 1915, is mathematically easier to work with than the ring singularity described by the Kerr solution, which is why physicists usually explain the properties of black holes to the public using the Schwarzschild model of a point singularity. For the same purpose of pedagogical simplicity, I will continue to refer to the singularity as a point of infinite density. So the simplicity of the Psyche equals singularity equation, the singularity described by Karl Schwarzschild, is a single point. And when physicists like Michio Kaku and Brian Greene and Leonard Susskind, they talk about it as a point. Although they also mention, according to the Kerr theory, the Kerr exact solutions to the gravitational field equations, the singularity would be a ring if the black hole is spinning. So discuss this a little bit, and rather than confuse us, just having said that, I'm going to move to the next slide. Echo of the Big Bang. Cosmic microwave background radiation, that's CMB radiation. Another powerful piece of evidence for the existence of a gravitational singularity came in 1964. Two radio astronomers and subsequent Nobel Prize winners Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation left over from the Big Bang. Working for Bell Laboratories, they were seeking the source of a strange background static being picked up by their Horn telescope used for radio astronomy in Holmdel, New Jersey. So we're just going over the history of the idea of the gravitational singularity, and the theory of the Big Bang gathered more evidence in 1964 when these two scientists discovered that in every direction in space exists this cosmic microwave background radiation. They were picking up static. They were trying to develop one of the earliest satellite communication systems for Bell Laboratories, and they were picking up static coming in from everywhere. They wanted to discover what's the source of the static, so they're using this radio telescope that picks up these. I don't know much about radio telescopes versus gravitational wave telescopes versus mirror telescopes. I studied philosophy and religion, and I studied physics to learn about the parallels and implications for philosophy. But at any rate, I know one of the stories they tell about this discovery was that they were trying to account for this background radiation by seeking defects in their telescope, and they had to clean out all the pigeon droppings from it, and they thought that would get the job done. But ultimately, accidentally, they discovered that this is the echo of the Big Bang. So if there was a Big Bang, then there was a singularity from which it banged, although even that point is contentious for reasons that we will see. Penrose and Hawking, black holes and the Big Bang. In 1965, Roger Penrose and Stephen Hawking used Einstein's general theory of relativity to prove mathematically that singularities must exist in certain types of collapsed stars and at the origin of the Big Bang. Penrose proved Robert Oppenheimer's earlier claim that a star of sufficient mass must necessarily collapse into a singularity when it burns through its nuclear fuel. Hawking reversed the direction of Penrose's time dimension for a black hole to create a model of the Big Bang. So J. Robert Oppenheimer, on September 1st, was at 1939, the first day of World War II, published a paper explaining why a star that burns through its nuclear fuel must collapse into a gravitational singularity. Then Penrose mathematically proved that that must be the case, and he described a star collapsing into a singularity. Then Stephen Hawking, who had the same graduate advisor as Penrose, asked his graduate advisor, can I just reverse the time dimension of what Penrose is working on? He's describing a star collapsing into a singularity. If I reverse the time of that model, then we have a star expanding from a singularity, or, in other words, we have a model for the Big Bang. Later, we're going to see Stephen Hawking rejected the idea of a gravitational singularity, specifically because he learned about the Pope Pius XII, saying that the idea of the Big Bang is evidence for God. He'll say openly that, therefore, in light of the Pope's proclamation, which was made in 1951, before 1965, obviously, when Hawking was defending the idea of a singularity. But when physicists were recalled to the Pope's proclamation, then a lot of them said, yeah, maybe you're right, that does sound a lot like creation from the hand of God, so maybe there was no singularity. In fact, there must not be. It's a theological bias more than any kind of an insight from the mathematics of physics itself. John Wheeler popularized the name black hole. So we're studying the history of the concept of a gravitational singularity, and he's an important physicist in the history of black holes. In 1967, the American physicist John Wheeler popularized the term black hole. He also came up with the term wormhole and quantum foam. He furthermore came up with the delayed choice quantum eraser experiment, a variation of the two-slit experiment. Stephen Hawking referred to him as the hero of the black hole story. So obviously, for a class describing the hero's journey through philosophy, cosmology, and philosophy, psychology, and physics, to see Stephen Hawking call John Wheeler the hero of the black hole story, it's important to mention that. Quantum entanglement, spooky action at a distance. In 1935, Einstein and two colleagues wrote a paper about what is now called the EPR paradox, Einstein, Podolsky, and Rosen. In that paper, they said any two particles, they were analyzing the equations of quantum mechanics, and they were trying to detect flaws, and this is what they discovered in the equations for quantum mechanics. It implies that any two particles that were ever in contact maintain an immediate connection no matter how far apart their later separation. What you do to one particle is instantaneously correlated with the partner particle. If you spin one particle in a pair of previously connected particles, the other instantly spins in the opposite direction. So quantum spin is not like the spin of a top as I have here on this image, but I'm just trying to summarize in an image the idea of quantum entanglement. If you change the spin state of one quantum particle that was formerly in contact with another particle, even if those particles are on opposite sides of the universe, the other one will instantaneously spin in the opposite direction. So continuing in the slide, that implies that a signal is sent from one particle to the other at an infinite speed, which, to Einstein's chagrin, violates the absolute speed limit of light. So Einstein came up with general relativity, his theory of gravity, to correct Isaac Newton's theory of gravity, which indicates that the force of gravity travels infinitely fast between two objects. We talked about the thought experiment of the vaporized sun. According to Newton's theory of gravity, it's as if the planets are tethered by a gravitational cord to the central sun. And if the sun were to suddenly vaporize, then the planets would instantaneously careen out of their orbits, just like if you were swinging a ball at the end of a string around your head and then you let go of the string, that ball would shoot off. Einstein said, oh, well, that implies gravity travels infinitely fast, but nothing can travel faster than light. So therefore, your theory must be wrong, and he came up with the idea that gravity is actually curvature of space-time, and that more massive objects create a deeper indentation in the four-dimensional fabric of space-time, like a bowling ball in the center of a trampoline. So that when the sun were to vaporize in the thought experiment, that indentation in the fabric of space-time would rebound, and that rippling wave would travel at the speed of light until it reached the planets about 8 minutes for Earth. Okay, so that was why he came up with general relativity, to counteract the infinite speed of gravity. So when he discovered that quantum mechanics indicates that there's this infinitely fast connection, some infinitely fast force connecting particles that were ever once in contact, he thought, thus I've disproved quantum mechanics. However, as we'll now see, what he demonstrated was implied in the mathematics of quantum mechanics was subsequently vindicated by actual experiments. Quantum entanglement, spooky action at a distance proved. Although Einstein pointed out quantum entanglement to refute quantum theory, it was proven experimentally in 1982 by Alain Aspect at the University of Paris South. Physicist John Gribben concludes that if everything that ever interacted in the Big Bang maintains its connection with everything it interacted with, then every particle in every star and galaxy that we can see knows about the existence of every other particle. If psyche equals singularity, then not only are all psyches one because of Leibniz's principle of the identity of indiscernibles, which we're going to talk about at more length in a few slides, but because the singularity is a quantum particle, we are also all connected in an immediate way by quantum entanglement, no matter how much space-time separates us. This is another reason to love our neighbor as ourself and to love God as the supersoul in whom all souls are one. Okay, so if psyche equals singularity, and then if we take into account that everything in the entire universe was condensed in one singularity at the Big Bang, then the implication is that all of us were at one point united with each other. Therefore, no matter how far in space and time we're separated from each other, all of us are always in immediate contact because of the nature of quantum entanglement. The idea of Leibniz's principle of the identity of indiscernibles, I discussed it a couple of slides ago. We'll be discussing it more length in a few more slides, but just to recap this fundamental principle, which is so important for the equation psyche equals singularity, if you can't detect the difference between two things, says Leibniz, the great mathematician who co-discovered calculus at the same time as Isaac Newton, if you can't tell the difference between two things, then they are identical. You cannot tell the difference between two singularities. They're outside of space and time, so they can't be differentiated by spatial or temporal concepts, and they are a point of infinite density. So then they're identical. This is a paradox about the individuality of each psyche and yet the oneness of all psyches. The Gaudiya Vaishnava school of Vedanta summarizes it in the phrase achintya bheda bheda tattva, inconceivably, simultaneously one and different. In some inconceivable way, all of us are separate, individual, eternal, personal souls, or Atman, and yet we're also simultaneously united with one supreme soul, Paramatma. And that's why I say that this is another reason to love our neighbor as ourself, because all of us are contained in one singularity, and we are all in immediate contact with each other at all times and in all places, according to the equation psyche equals singularity when you apply the principle of quantum entanglement to the equation psyche equals singularity. The expansion rate accelerates. Hubble discovers dark energy. In 1990, the Hubble Space Telescope was put into Earth's orbit. Using that telescope, Saul Perlmutter in 1998 and Adam G. Rees and Brian Schmidt in 1999 led separate teams of physicists who unexpectedly discovered that the expansion rate of the universe is increasing. So they believed it would have been slowing down under the influence of all of the matter in the universe. The gravitational attraction of everything for everything else should be slowing the expansion rate down after the Big Bang, but they found that it was accelerating to everyone's amazement. They were studying type 1a supernovas, which serve as standard candles of luminosity in different galaxies in an attempt to measure the expansion rate of the universe, which they assumed would be slowing down under the influence of its own gravity. Instead, they discovered that the expansion rate accelerates over time. This was confirmed by photographs of the cosmic microwave background radiation taken by the WMAP satellite, which was launched on June 30th, 2001. So Einstein, you will recall, in 1917 inserted to his equations for general relativity what he called the cosmological constant, symbolized by the Greek letter lambda, which was an anti-gravitational repulsive force that he thought would counteract the attractive force of all matter for all other matter in the universe, which would be causing the universe to contract. He believed the universe is static, that it doesn't expand or contract, and so he inserted the cosmological constant to keep things in balance. Then in 1929, when Edwin Hubble discovered, using the 100-inch mirror reflection telescope on the Mount Wilson Observatory, he discovered that what they thought were just nebulous clouds of star gas were actually independent galaxies, and that each of them was accelerating from the other at a rate that increases in its proportion of the distance. So Hubble discovered that each of the galaxies accelerates away from all of the others at a rate that's proportionate to its distance from the Earth. So at any rate, he showed that the universe is expanding, and if it's expanding now, then in the past it must have been smaller, which confirmed Lemaitre's theory of the Big Bang from a primordial atom, or a gravitational singularity. As we discussed previously, Einstein accepted Hubble's discovery and then retrogressively accepted George Lemaitre's Big Bang theory, though he still disregarded the idea of a point of infinite density. And he then said that the insertion of the cosmological constant into his equations was the biggest blunder of his life because he didn't need this repulsive force of anti-gravity anymore. That acceleration, the universe was not static, it was expanding. So at any rate, now we're going to see that his cosmological constant is reincarnated as the dark energy of the quantum vacuum, which is we'll talk about in the next slide. Dark energy equals vacuum energy. As discussed earlier, the quantum vacuum beneath every point of 3D space is created by virtual particle-antiparticle pairs that pop momentarily into existence, then rapidly recombine and annihilate each other, creating vacuum energy in the process, which was confirmed by the Casimir experiment with two plates placed very closely together. We discussed that. Since the discovery of the accelerating expansion rate of the universe in 1998, vacuum energy has been called dark energy, which accounts for about 70% of the energy of the universe. Dark energy is also called the cosmological constant, the term Einstein first used in 1917. Quantum vacuum review, virtual black holes, and renormalization. So this is such a fundamental piece of current cosmology. And we're going over the history of a gravitational singularity, and it appears that there are gravitational singularities at every point of the quantum vacuum underlying every point of three-dimensional space, so it's worth reviewing this fundamental concept. In review, quantum theory indicates that there should be an infinite amount of energy in the quantum vacuum caused by high-energy virtual particles colliding together to form miniature black holes. Infinite magnitudes destroy the predictive power of physicists' formulas, so they invented a mathematical trick called renormalization to ignore the miniature black holes that emerge from and apparently carpet the quantum vacuum. According to Susskind, the result is no longer infinite, but it is also now small. The estimate that quantum field theory gives is so big that it requires a 1 with 116 zeros after it. 10 to the 116th power, he says with an exclamation point. Now notice I include the subtitle here, The Cosmic Landscape, String Theory, and the Illusion of Intelligent Design. I included that subtitle because, as we're going to see, the extreme precision of this number representing the cosmological constant that determines the expansion rate of the universe is so precise that it seems impossible that it just randomly emerged at precisely that extremely unlikely number, giving rise to intelligent design theories. Susskind admits, yes, it is so precise, it seems impossible that that could be random, which is why he gives the subtitle String Theory and the Illusion of Intelligent Design. There is the illusion of intelligent design. It does appear that the universe is intelligently designed, says Leonard Susskind, the atheist. He'll go on to explain that string theory, as well as quantum theory, indicates a multiverse of universes. If it's not an infinite number, then it's 10 to the 500th power types of different universes, and then innumerable actual universes within each one of those types. But most likely, if there is a multiverse, it is infinite because they emerge from gravitational singularities, which are themselves infinite. Physicists are constantly trying to tame infinities for a good mathematical reason. Nevertheless, I'm arguing that the gravitational singularity really is a point of infinite gravity, and it is the psyche. And each psyche or soul is part of a supreme psyche, and the whole class is designed to help us realize that we are these eternal servants of God, and that whether that is true or not, psychology in the 20th century came back full circle to the realization that humans cannot be happy unless, or at least humans can't achieve the ultimate happiness without perceiving ourselves to be eternal, immortal heroes serving God on the cosmic stage. So we're constructing the cosmic stage to perform our heroics for God and to convince our scientific minds that this is a plausible belief, that each of us is a gravitational singularity, a spiritual conscious being united with the omnicentric singularity. And here we see Leonard Susskind saying, yeah, it does seem that the universe is intelligently designed. However, it's not intelligently designed because there's an infinite number of parallel universes, and even though it's almost infinitesimally likely that this universe would emerge with just the right cosmological constant for life to exist, given an infinite number of throws of the coin, it's going to come up sometimes on exactly the number it needs to be. So the enormous number of parallel universes accounts for the fact that this particular universe seems to be so precisely fine-tuned for life. We're going to talk about that more in the next slide, but this is an overall review of the importance of understanding the physics of the quantum vacuum. So continuing here, Leonard Susskind talking about what the vacuum energy is, even after you renormalize away the miniature black holes, it's still this enormous number. He says, it is far more energy than all the stars in the observable universe will ever radiate in their entire lives. So the equations of quantum mechanics and string theory, as we'll see later, predict an infinite amount of energy at each point of the quantum vacuum, which means that each point of the quantum vacuum is a gravitational singularity. After renormalization, the number is still this enormous number, one with 116 zeros after it. That is what the equations predict. However, the observations through the WMAP satellite and the Hubble Space Telescope indicate that the quantum vacuum energy must be very, very small. And Susskind quoted somebody where he called it the worst prediction ever, that the equations predict an enormous amount of quantum vacuum energy, but the observations indicate it must be some infinitesimally small, minuscule number. And he's going to call that the mother of all physics problems. The cosmological constant, mother of all physics problems. Some of the energy in the quantum vacuum is positive, photons and other bosyons, and some is negative, electrons and other fermions. So they balance each other out almost perfectly. So there's two basic types of virtual particles in the quantum vacuum, bosyons and fermions. Bosyons are positive, fermions are negative, so you would think they would cancel out to exactly zero. And they do almost cancel out to zero, but not quite. So continuing here, the overall vacuum energy density must be incredibly small to fit the observed data. A decimal point followed by 118 zeros and then a 1. No one knows why so many huge sets of numbers cancel each other out to such an absurdly minuscule but non-zero number, which is called the cosmological constant, which Einstein originally inserted into his equations in 1917 as a repulsive force of gravity, then removed in 1929 after Hubble's discovery. Susskind says it truly is the mother of all physics problems. So, the mother of all physics problems is the quantum vacuum, and why the observed data indicates that the energy in the quantum vacuum is this extremely tiny number. A decimal point with 118 zeros and then the number 1. We saw that the equations of quantum theory indicate that it should be 1 with 116 zeros after it, but instead it's the exact opposite, almost, with 118 zeros after a decimal point. So at any rate, it was called the worst prediction ever by one physicist. I read the quote earlier, that of all of the predictions of quantum theory, the prediction of how much vacuum energy there is the worst one ever. It's this extremely tiny number. But more curiously still is why it is that extremely tiny number, but not exactly zero. That's the idea of fine-tuning. It seems too improbable that it would land on just that precise number. And if it was any bit more or less, then the physical constants required for life to emerge, biological life to develop, would have emerged. There'd be no life. So it seems as if the universe is intelligently designed, and the biggest evidence for a cosmologist is the vacuum energy density, which is this extremely small number. So I'm going to read here a little bit from The Cosmic Landscape, where Susskind describes that. He says it's the mother of all physics problems, so it's worth reading a little bit from the expert here. A lot of these details baffle my mind. We don't need to have a perfect knowledge of these concepts, but it's good to have at least a foundational beginning introductory knowledge, because we'll be referring back to them throughout this entire class. So reading here from The Cosmic Landscape, String Theory and the Illusion of Intelligent Design, this is page 77. The vacuum energies of fermions and bosons do not cancel, and the bottom line is that our best theory of elementary particles predicts vacuum energy whose gravitational effects would be vastly too large. We don't know what to make of it. Let me put the magnitude of the problem in perspective. Let's invent units in which 10 to the 116 joules per cubic centimeter is called 1 unit. Then each kind of particle gives a vacuum energy of roughly a unit. The exact value depends on the mass and other properties of the particles. Some of the particles give a positive number of units and some negative. They must all add up to some incredibly small energy density in units. In fact, a vacuum energy density bigger than, and he's got a decimal point, he's got 118 zeros and a 1 units, would conflict with astronomical data. For a bunch of numbers, none of them particularly small, to cancel one another to such precision would be a numerical coincidence so incredibly absurd that there must be some other answer. Why is this number the one upon which the cosmological lands? If it was any bigger or smaller than this extremely precisely small number, life would not have emerged. So continuing here, the physicists, myself included, looked at the absurdity of the required coincidence and said to themselves and each other that there must be some deep hidden mathematical reason why the cosmological constant must be exactly zero. This seemed more likely than a numerical cancellation of 119 decimal places for no good reason. We have sought after such an explanation for almost half a century with no luck. He wrote this in 2006, so it's even more than half a century now. Finding the reason has been regarded as the biggest, most important, and most difficult problem of modern physics. No other phenomenon has puzzled physicists for as long as this one. Every attempt, be it in quantum field theory or in string theory, has failed. It truly is the mother of all physics problems. Fine-tuning argument for God's existence. For biological life to exist on Earth, the various physical constants of the universe, the speed of light, the fine structure constant, electron mass, etc., have to be exquisitely balanced in a way that seems too statistically unlikely to have occurred through a random process of evolution, which indicates that they were intelligently designed, presumably by God. Of all of the precisely measured constants of nature required for biological life, the cosmological constant is the most precise and therefore the least likely to be random. That again is why Leonard Susskind subtitled his book, The Cosmic Landscape, with String Theory and the Illusion of Intelligent Design. In this picture you'll see there that's supposed to represent the hand of God, and all those dials on the background represent the constants of nature. Each one has to be just precisely what it is, no more or less, or the laws of physics wouldn't allow for biological life to exist. For this class, the fact that Leonard Susskind, an atheist and a Darwinist, admits openly that the universe seems to be intelligently designed is important, because we're trying to create a stage using cosmology upon which to perform our heroics for God. That's the goal of the class. So this very intelligent co-founder of string theory is admitting, yes, the universe does seem to be finely tuned by some intelligent designer. However, because there's a multiverse, it can emerge randomly. As we'll see later, the Vaishnava branch of Hinduism and Hindus generally perceive the universe as one bubble in an ocean of bubble universes. They also have a multiverse theory. All of the bubble universes are exhaling from Mahavishnu, who lies down on the causal ocean. So that's another irony, that in the attempt to disprove what he calls the illusion of intelligent design, Leonard Susskind, with his holographic string theory embedded in the overall multiverse theory, has rediscovered the ancient Hindu cosmology, where the cosmic horizon of each spherical universe contains the past, the present, and the future. It's called Akasha. And these threads, Sutratman, these thread souls, radiate in the illusion of the material world. So we will be discussing that later, but I just wanted to point that irony out now. I hope you are enjoying this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. You can also click the link to my website, psycheandsingularity.com, to sign up for a multiple choice test with over 100 well-crafted questions related to this class, and links to the specific parts of each video where the answers can be found. If you take that test to the end, you will receive a certificate indicating that you have become a Psyche and Singularity scholar. In addition to access to that test, there is also the opportunity to answer essay questions that ask you to relate concepts covered in this class to your own hero's journey. I will personally respond to each of those essays, point out any other parts of this class that I think might bolster your plan. Finally, I want to point out that this course is sponsored by the Platonic Mystery School of the Divine Infinite Being, and you can check those guys out at divineinfinitebeing.com.